Okay, you're recording. Good. Now, so what are we going to do today? We are going to look at some tests. We will start with the impact test. We are going to see together. Then I am going to elaborate on the test as well with you as it goes or towards the end. We will see. This printer has to stop. I'm not sure if you can hear this voice or not of the printer working. But anyways, we will start. Before we start, guys, you're hearing me, right?
ايه دكتور.
تمام.
يس دكتور.
انت كلامي واضح. انزين انا الحين بشغل الفيديو، ابغى اشوف تسمعون الفيديو ولا لا؟ قولوا لي لو سمحتوا. يعني we will just give it a try الحين and make sure that you are listening.
The Ch.4 impact test.
Could you hear this؟ ها؟
سمع واضح.
انزين ازيد بالصوت مثلا تبون؟ يحتاج ازيد بالصوت؟
واضح دكتور الصوت.
اوكي.
ما يحتاج ازيد. طيب. So we will see the impact test now together, how it is done. Then we will have some يعني discussions about it. Then we will go to the hardness test after that. It's a short video. It's not a long video. We will see it together and then we will discuss it and then we will go for the next one and discuss that as well. البرنتر باقي له ورقه بيخلص. Yes. I wanted to shut off so that we can. Yeah, one paper only to go. But hopefully it will not be disturbing much. Yeah, let's go. Let's hit it.
The standardized Ch.4 impact test has been designed to measure the Ch.4 impact test. The standardized Ch.4 impact test.
First of all, before we start, how many type of impact tests do we have?
Two.
Which are?
ايزوت.
What?
Sharp isot.
And Ch.4, which the one we are going to see in this test. The isot we are not going to see. The difference between them is just the position of the hammer and the type of the specimen. How do we put the specimen on the machine, the impact test machine? So that's the difference. We are going to see a Ch.4 impact test now. Yalla, go ahead.
Has been designed to measure the toughness of materials under impact loading and multi-axial stress state. A pendulum impact testing machine is used to do so. The pendulum on the machine has a heavy weight at the end. This is lifted into the starting position in step 1. Then the tester checks whether the testing machine has been adjusted accurately. In order to do this, he turns the drag indicator downwards and releases the pendulum without a test specimen. The drag indicator stops at position 0. This proves that the pendulum has the correct starting position and that the friction is correctly compensated.
The first thing that is done here, just to see that because when you do the impact test, actually the machine itself could be old, مثلا, or the oil is not put good. So it depends actually in recording the impact test on the energy of the hammer. So it needs to make sure that the scale which you have in front of you here shown now, it's well calibrated, that it starts with 0, not with another number. That's number 1. Number 2, that the lubrication is done good enough as it would not take as part of the impact energy of the material. Yani it will not, the lubrication is good enough not to resist the motion of the hammer. So this is what is made sure at the beginning, that it is going to a 0 when it's going to a 0 at the beginning, as you could see there, with a free hammer, with a free movement or with a free fall, no energy is absorbed. So it shows that it is 0 there. So this means that we have a good machine there. The lubrication is good. That's to start with.
The machine is ready for the tests. First test, strain-aged plain carbon steel S235.
So the material which we are going to use in this one will be plain carbon steel, but it is strain-aged. And you can see here this designation is not something you used to, صح? When we say plain carbon steel, what is it for the AISI? If we know this, for example, that this is let's say 0.1% carbon steel, it will be AISI 1010, right? This is another designation. It is S235. Of course, this is a strain aged, and strain aging means what? Anybody? يعني شنو strain aged? No one? Strain aged means that it is strained in order to make it stronger. And in addition to that, it is aged as well. يعني you have some thermomechanical process done on the material. When you strain it, this means that you are plastically deforming it. By plastic deformation, we introduce dislocations, صح? With introducing dislocations, you are making the material stronger, صح? Which we also refer to as work hardening. And then work hardening, we have cold work and we have hot work. This is a kind of hot work, actually, because when you say aging, it means that it is aged, and there is something which is done thermally there as well. And the designation that we have here is different. I brought it from a British institute who is putting this video there. So this is a British we have the S235. It is a steel. It's called structural steel. S stands for steel, but there are other designations which are not shown there in that system or that standard. There are different standards. This standard I can send you if you want. You can look at the standard itself. It has different designations than what we have taken there. So I can send you the link here for this one as well in order to see the designations there. So let us continue with this. So this is a plain carbon steel which is strain aged.
This is our test specimen.
This is, you could see, this is the test specimen. You have a V notch specimen here. So that V is made there in order to do the testing of the impact test. Now the question, why, and this question could be in your test, صح? Next test, why do we V notch it? Why do we V notch?
Because it has to failure at some point, or the specimen has to fail.
Grammar. Who is speaking here?
Khalid,
your grammar. You say it has to fail at some point. Not it has to failing, صح? It has to fail at some point. It has to fail at some point. It also, in addition to what you said, I want it to fail at this position only. So it has to fail so that it does fail. It does not jam the hammer there. That's number one. Second, I want it to fail here specifically. صح? And this V notch is made with specific dimensions, ولا anybody does his own dimension?
No, في specific dimension.
Specific dimension? Why? Why don't everybody does his own dimension يعني?
Standard.
Standardized. Otherwise, our test results will be different, صح? So let's continue.
It has been machined to standardize size and shape with the characteristic V-shaped notch. The tester places the specimen on a support in the lower part of the machine and adjusts its position.
Notice how he is putting it. Of course, he will use a tool which he has in order to put this in the middle, so that when the hammer hits, it hits in the middle there. That's number one. And also notice that this is the Ch.4 position. The Ch.4 position, the specimen is put horizontal. That's number one. Number two, the hammer comes from this side. You can see my mouse, صح ولا لا?
Yes, we can see.
Yes, the hammer comes from this side. So it comes from this side and hits. You see the notch is on the other side. Why do we do that? Because we make sure that this notch will open up when the head is from this side. But if the notch is on the other side, of course, it's not going to open up and it might jam. The use of the notch will be obsolete. So let's continue.
With a centering device. Next, he turns the drag indicator downwards again and checks that everything is prepared correctly.
Of course, this is the position which is set for the Ch.4. The position which is set for the isotope is a bit different. It's like that. The height is different. So this is one difference between the Ch.4 and the isotope. But this uses, they are using Ch.4 now.
Perfect. The test can begin. The pendulum is released, it swings downwards and hits the specimen with its rounded hammer peen. The specimen absorbs part of the pendulum's energy, so the pendulum doesn't reach the full height on the other side. The amount of energy that has been absorbed by the specimen can now be read off at the position of the drag indicator. It only amounts to 13 joules in this test.
That is 13 she meant, right? So every digit 1, 2, 3, 4, 5. So this means that from 10 to 20, if you have 5, so every one will be 2 digits, and this is 2, and this is 4. So this is actually 10, and that is 13. This is what she meant. Now this means actually this scale is calibrated in a way that it calculates directly how much energy was absorbed in joule by the specimen that you are putting here. We will look at this also again. So this is the number of joules which were absorbed by the specimen, and this should have come where, if you did not have a specimen, this should have come to 0, because energy, when it is falling, it has a certain energy, it hits the specimen and it goes back. When the specimen is there, when the hammer is there, it hits and it goes back to its initial position, the same height. But it did not. It hit the specimen, some energy was absorbed, and it went back to a lower height. The difference between the initial height and the last height, as we have seen in the theory, is used to calculate the difference in the energies, and it is calibrated there directly in this scale which is given. The energy which is lost is nearly 13 joules. It will show now.
Here is the main principle of the measurement. In its starting position, the pendulum only has potential energy. It is given by mass of the hammer m times rotational acceleration g times starting height capital H. After the pendulum has been released, the hammer moves downwards, hits the specimen, and then only swings to height small h. Exactly at the first reversal point, the pendulum again only has potential energy, which is m times g times small h. The energy that has been absorbed by the specimen is called notch impact energy, kV. It corresponds to the difference between the two potential energies.
You see, the difference in the energies is not the mg, it's only the h which we have here. A capital H for the initial height, and the small h for the final height which we have. So somebody might wonder, what is the difference between the two? It's the h here and the small h here. The difference between that h, it has that much energy. The energy which it has here, it has a small h. So the differences in the energy is the energy. The differences between the energy at this position and that position is the energy which is absorbed by the specimen. And this is how the energy absorbed by the specimen is calculated there.
The first specimen only shows very little plastic deformation. A mostly flat, slightly glittering fracture surface has been formed. This is another important indication that this kind of steel is only able to absorb small amounts of notch impact energy. It shows mainly brittle behavior due to the strain aging effect.
Now, you can see when we strain age, when we cold work any specimen and age it as well at the same time, it causes the material to kindly embrittle. We don't say it's very brittle. It has some deformation there, but like when we talk about carbon, when we increase the carbon content in our steel, what does it do? Material does, of course, the material, even with the 0.8% carbon steel, is not a brittle material because it has a good appreciable amount of plastic deformation happening there. But what we say it embrittles. Embrittles يعني شنو؟ It's going towards the brittlity. يعني قاعد يتجه بذاك الاتجاه as we increase the carbon content. Here now, when you strain age the material it embrittles. This is what she is saying here. The shape of the failure and impact when you have that side and you have a strained edge like that, and the failure occurs like a clear, which you can see here, like a clear cut. This is an indication for a brittle failure. Like in the tensile testing, if you remember, we had a clear cut and we had what kind of failure there, Bad?
Cup cone.
Cup cone. A cup cone was an indication of a ductile failure, and a clear cut was an indication of a brittle failure. So here also we have the same thing. This clear cut is an indication of a brittle failure of the material. So let's continue. And by the way, before we continue, the energy which is absorbed, which you notice was 13 joules, which is little, which is absorbed by the material. The more the brittle the material, the less the energy it absorbs actually. So we will compare now with a more ductile material, but a strong material, which is the normalized steel. Let's continue.
Second test. The second specimen has been made from normalized steel S235. It is also placed on the support and centered. The tester turns the drag indicator to its starting position, rechecks all safety measures and releases the pendulum. This time the impact sounds much deeper and richer. An impressive energy of 182 joules has been absorbed by the specimen. Here the specimen did not break into two pieces. Instead it was pushed through the counter bearings under heavy plastic deformation. In comparison with the strain-age steel, the normalized steel absorbs much more notch impact energy and behaves in a very tough manner.
You can see the difference between this surface. It went through a big, it seems like you don't have a straight cut, first of all. It went through a huge plastic deformation and still it did not cut, basically, as you can see here. The energy which is absorbed by this material was nearly 182 joules, which is much bigger than the 13 joules which is absorbed by this specimen. Now then you can clearly see that this material is a ductile material. This is a ductile failure. This is a brittle failure. Brittle materials have very low toughness compared to the ductile materials, but of course the ductile material has to be also strong in order to absorb energy. Therefore, as what we have covered in theory in the class, what does the toughness of the material rely on? Two things.
The stiffness of the material and the ductility of the material.
No.
Temperature.
Ductility is correct, but not the stiffness.
Strength.
Stiffness is different than the strength. Why are you taking material science? To distinguish between the stiffness and the strength, right? Stiffness is something related to the bonds between the atoms. The strength is resistance to plastic deformation, isn't it? So those are two different things. Yeah, so it depends on the strength. It's a combination between strength and ductility. The materials with high strength, like this material is a brittle material. It has high strength, but the ductility is low, toughness is low. This material is strong in strength and ductility as well. So you could see the toughness is high. Let's suppose that we are talking about a polymer. Polymer has high ductility, but low strength. If you test the toughness of it, it will be again as small as we have in the case of the brittle materials as well. Okay, so let's continue.
The Ch.4 impact test is not only carried out at room temperature. Materials with body-centered cubic crystal structure, such as plain carbon steels, show a characteristic S-shaped curve of the impact energy versus temperature. In the so-called upper shelf region, the material absorbs a lot of energy and behaves in a tough manner. At low temperatures, in the lower shelf region, only a small amount of impact energy is absorbed and brittle fractures occur. Metallic materials with a face-centered cubic crystal structure, on the other hand, do not experience a ductile to brittle transition. These materials retain their ductile behavior towards low temperatures and are therefore well suited for low temperature applications.
So as you can see here, you have the upper shelf and you have the lower shelf. Some materials like the BCC crystal structure that we have already covered, for example, the BCC, the steels, for example, the alpha steels at room temperature, for example, they have a big S-shaped behavior there. Sorry for this. I think this is the tip calling me. I'm going to close the sound. Okay. الو. نعم. قلت لكم الشيخ انا الحين في وسط محاضره، ممكن تكلمني عقب ساعه لو سمحت؟ في وسط محاضره انا الحين. مشكور حبيبي، شكرا. I am having a problem with internet. I'm very sorry at my home. Sorry for the interruption. So it has upper shelf, يعني it has high toughness as we can see here, the BCC crystal structures. But there is a temperature which we refer to as the transition temperature. The toughness of the material reduces drastically. The ductility of the material reduces drastically. Because of that, the material becomes actually brittle at low temperatures. And this is what causes the loss of toughness of the material. So we need to be careful. On the other hand, materials with the FCC crystal structure, actually it's not like that. There is some loss of ductility, of course, it's there, but the loss of ductility is very little. And this is a concern that we have when we talk about toughness and reliance on the transition temperature that they have. So this is just to show that this is not made by me, by these people. So I wanted just to, this is copyright. I wanted to show that. Any question about the impact test, please? Any question about the impact test? Are you guys with me?
Yes, doctor.
Okay. So any question about the impact test?
دكتور
أيوة.
لما المطرقة تطق القطعة وين تروح؟ تنفلت ولا تلصق ولا وين تروح؟
يعني إذا انقطعت كامل it will fall in the machine there, or if it is not like that, it might get held somewhere here or there. مو مهم هذه مهم.
Okay.
Okay. Any other question? Is the impact test clear?
Yes, doctor.
Okay. If no questions, then we will start now with the hardness test. We want to see the three hardness tests that are done. We will look at the hardness test now.
The Brunel hardness test.
So we have, how many types of hardness tests did we look at in theory in the class? Brunel, Rockwell,
4.
Pickens, and Noob. All of them, right? We will see three of them. Then now we will look at those.
Using the Brunel method, the hardness of a turbocharger housing is to be measured. First of all, the tester has to make himself familiar with the testing machine. A monitor and the control panel are positioned in the upper part of the machine. These are used to select and program different testing methods. Below the control panel, a microscope lens with a digital camera and an indenter are installed. These two elements are connected to each other and rotate towards the test piece as required. It is also possible to select and exchange the indenter, so different methods of hardness testing can be conducted on the same testing machine. The support table can be adjusted in height, so the test piece can be positioned at the correct distance to the microscope lens and the indenter. After becoming familiar with the machine, let's start the experiment. The principle of the Brinell hardness test is to press a hard spherical indenter with an exactly defined force onto the test piece, then evaluate the surface area of the indentation. The tester selects a suitable spherical indenter and inserts it into the holding device of the testing machine. Next, he puts the turbocharger housing onto the support table, rotates the microscope lens into vertical position and adjusts the correct height of the test piece. After bringing the test piece surface into focus, he selects the exact spot where the hardness test is to be made. By pushing the start button, the hardness test procedure begins. The testing machine rotates the lens back to its resting position and places the spherical indenter carefully on the test piece surface. Gradually and shock-free, the test force rises to its specified value. After maintaining the test force for a certain time, the indenter automatically lifts off again. The lens pans back to its former position. The indentation can now clearly be seen on the monitor. With the control knob, the tester places 4 measuring lines.
You can see. Now, indentation, and that's the same philosophy for all the hard testing machines actually, that you use an indenter, you try to indent the specimen by a certain force. Of course, it differs from one to the other one. And once the indentation is done, indentation and the indenter sizes are used normally, and the force are used to determine the hardness number. Now, in this case, in the Brinell, you can see those lines there are used in order to measure the diameter, which is caused the diameter of the indentation, which is caused by the indenter. So you notice that those he will put them there, and then we will just click on the machine. It will record the diameter, and it will be using it in the calculation. Without doing the calculation, the machine does that itself and gives you a number. This is done.
On the edges of the indentation to measure its diameter. That's it. The testing machine can now calculate the Brinell hardness. The hardness value is defined as test force F in the old unit kilopond divided by the area of the indentation A in square millimeters. The result is displayed on the bottom left-hand corner of the screen and amounts to 250.
Let me just remind you something. I mean, just where is that? I can just show you the table in chapter 6 here, so that to remind you of what we are doing here. We are is it opening? No? It's not opening. What? No, is it? Let's close this. All right. Yeah, okay. I wanted actually that. Let me close that one. My goodness. Don't see. All right. I wanted just to look at that. This is what we are looking at. We started with the Brinell. Actually. We saw that those are the dimensions. This is how it is done. Then that dimension is used. The force is used with this calculation actually. With the dimensions of the diameter of the indentation and the diameter of the indenter. So what she is saying that is not very correct. So I just wanted to for you to bear in mind that the formula which is used in order to calculate that is not that. I noticed that in all the hardness test, the formulas that they are using is not very correct. This is the Brinell hardness number, and it's not the area which is used there. Is d square minus d small square. So that capital D is for the indenter and small d is for the indentation. So that's basically like the area, and that is the force which is used there. Okay. we just need to be careful. I wanted to just notify you with that so that you don't say I did not tell you. So this is for the Brennan hardness test. And also another thing we just wanted to look at there in the next page, you could see the Brennan hardness test. You use the highest level of forces from 500 to 3,000 kilograms. It depends on what you wanted to test basically there. You can change that in increments of 300 or 500 basically. So this is called the Brennan hardness test. Let's go to the next one, which we refer to as the Rockwell hardness test. And let us look at this one. Any question before we proceed?
دكتور نقدر نستعمل سبيسيمن ما في يعني؟
The nice thing, yes, the nice thing about the hardness test, it is very simple as you have seen, and it's very low time consuming. In this case, you did not even want to prepare the specimen for something, since it has a base that you can push on. Khalas, finish. You can use it. In addition to that, is what you are saying. It's a non-destructive test. Yani the specimen that you brought, you did the hardness test on it, you will use it in the car and wherever. It's not damaged, right? So it's called the non-destructive test. Yes, you can reuse it. Okay? Let's go to the Rockwell hardness now.
The Rockwell hardness test.
Remember, the Rockwell hardness test has different scales. Let me return you back to the table so that you remember. This is the Rockwell hardness test. As you can see, the Rockwell hardness test has different scales. If you remember, scale A, C, D, B, and so on and so forth. For each one of them, you have the cone is different, the dimensions are different, and loads are different as well. So in this case now, we are dealing with, we are in this case,
scale C.
We are looking at.
In this video, we will show how the Rockwell hardness test works using a gear wheel. The basic idea of this test method is to measure the permanent depth of indentation of a hard indenter under a test force. In the process variant scale C, a rounded cone made of diamond is used as an...
So the diamond indenter here is used. Add to that, in this test, there is something special which is advised, and this is done actually by the machine in order to increase the accuracy of this test basically, and you will see it in a minute.
Indenter. In step 1, the diamond cone is pressed onto the test piece surface with a minor force of 10 kilopons. The depth of indentation under this preliminary load is the reference point. In step 2, the test force is increased by 140 kilopons, which is acting as the major force.
This is what I was saying. There is the initial minor load which is applied at the beginning, and then there is the actual final load, major. It's called the major load which is applied. This initial load is actually a load which they apply in order to increase the accuracy of the measurement, and it's kept until the measurements are done basically, and then it is removed. This is done in order to test them, to do the testing, and this is called the major load which is applied there.
This means that an overall force of 150 kilopons is now acting on the indenter, and this force is held for a certain time. In step 3, the major force is removed again. While the minor force is still acting, the permanent increase in depth of indentation E is measured. This is how the Rockwell hardness is calculated. Rockwell hardness HRC is equal to 0.2 minus permanent depth of indentation E in millimeters.
And this formula is correct. You just need to manipulate that for the formulas that we have in the table. That this formula is correct. The previous was not, and the next one which we will see is not.
Times 500. Let's take a look at how the test is carried out in practice. The tester selects the conical diamond indenter and installs it in the testing machine. Then he picks up the gear wheel and puts it on the support table. After rotating the microscope lens to its vertical position, he can adjust his test piece. As soon as a focused image can be seen on the screen, the surface of the test piece is in the correct height. The test can start. In modern testing machines, the Rockwell hardness test is fully automated. That's why the Rockwell hardness test is used so often in automated production lines. That's it. The Rockwell hardness of our gear wheel is 55 HRC. This result is displayed on the screen.
You can see, very simple. We just put the specimen there, plugged in the machine, does everything, so it records for you the hardness Rockwell on scale C. It has given you. So very simple, and that's why the hardness tests are actually cheap and inexpensive as well, and that's why they do it. So any question about the Rockwell? We have one more to go, which is the Vickers, and we will finish. No questions. Let's go to the Vickers hardness test. Again, I will just look at
the Vickers hardness test.
Okay, what happened there? Something wrong happened. Where is the? Yeah, this is the one, and that is the Vickers. And the Vickers hardness test is like the noob, as we say, and we will see why. So that is in the table. I'm just reminding you of what we are doing.
Hardness of a compressor wheel for a turbocharger is to be measured using the Vickers method. The main principle of this hardness testing method is to press a pyramid-shaped diamond indenter with an exactly defined force onto the test piece, and then to evaluate the surface area of the indentation. First, the tester has to prepare his testing machine. He takes the Vickers indenter with the four-sided pyramid and inserts it into the mounting device of the testing machine. He then places the compressor wheel on the support table and rotates the microscope lens into its working position. With a hand wheel, he adjusts the height of the support table until the test piece surface is displayed in focus on the screen. Next, he moves the test piece around on the support table until the right spot for the hardness test is displayed. Now that everything has been prepared, let's begin with the test. After pushing the start button, the diamond pyramid pans down and carefully touches the test piece surface. The test force slowly increases to its specified value. After holding the test force constant for a certain time, the indenter lifts again, pans back, and the microscope lens resumes its former position. This is the magnified indentation on the display screen. With the control knob, the tester now places 4 measuring lines at the corners of the indentation. Doing that, he can easily measure the length.
See, the corners are measured from here to there, and the corner from here to there actually. So actually the diagonals are measured here of the indentation which you have here, because we have a pyramid. Now, question: what's the difference between the Vickers hardness test and the Rockwell and the Brenner hardness test? What's the difference between them? The major differences between them, of course, in the shape of the indenter, there is a difference. But what distinguishes from the other two, the Vickers? Anyone?
يتم مبدا ماسك في الماتيريال او specimen.
No, we actually push it and keep it like that for a while, and then we remove it to measure this. And this is actually, in this case, this is what they suggest, that it increases the accuracy. But the major difference is that this is called a micro hardness test. The indenter is much smaller. The indentation, the indentation which is called, of course, will be small. The load which is used for the indentation is much smaller as well. In the Brenner, we have big amounts of loads which we have there, from 500 kilograms and so on. In the Rockwell, we have up to from 150, like that. That's the range, and a little bigger. And here we have 1 kilogram not more than that as indentation. This is called a micro hardness test due to that. But I wanted to notice that in the measurement you are measuring the diagonals, because she will say now how to measure that. Also the equation is wrong.
Of the two diagonals. Finally, he only has to push the input key. The Vickers hardness value will then be calculated automatically. It is equal to the test force F in the old unit kilopond divided by the area of the indentation A.
This is not correct. You will see in your so anyways, this is it for that, for this, because this is the indentation. We make it bigger. For the Vickers, that is, this D is actually the average between that diagonal and this diagonal. It's never the area. That is the diagonal square, the average diagonal square. This number is also in the book here. It's wrong. It's 1.854 basically, and this table is wrong, and the number is given in your text. You will be correct. Okay, so it's not the area there as well. This we come to. We have seen just
in square millimeters.
Just a few things about this. Is finished actually. The video, I guess, it's finished. We don't have anything else. Yeah, it gives the number directly there. Oh yeah. Let's just look at it also.
Hardness of our compressor wheel is displayed on.
Yeah.
The Vickers hardness of our compressor wheel is displayed on the bottom left-hand corner of the screen and amounts to 125.
You do one thing. Some of the things that I want you to observe is that we cannot, although there are charts to compare this with this, to correlate the numbers together, I wouldn't really do that, because this is, and even they, when they are doing that, some people are doing that, they do really say that caution has to be exercised a lot when you compare the numbers. It's not correct, actually. Fundamentally, this is my point of view, to compare the numbers there, because you're using so much different dimensions, loads, equations, so it's not comparable. Actually, you cannot compare the values there. That's number one. Number two, in the impact test that we were doing there,
the Ch.4
test that we did there, if we see, let's say, the specimens that we see, when it gives the, when you get the energy in joules of the different materials, you need to also do something, because maybe the size here of this specimen is different than the size in that specimen. Or well, we standardize it. That means that we don't have differences, do we?
Tolerance.
There is always tolerance there, and even in the V shape that we are making, is it correct? 100%? No. So in order to reduce the differences, we need to take that area. We divide. Let me go to the specimen itself. Not yet. Just to show the specimen. Yeah, that's good. When it comes to the reporting of the value of the toughness, normally we say the energy which is absorbed divided by the cross-sectional area. If you cut from here, you see the cross-section of that. But obviously, that is the cross-section that we will be using, the minimum cross-section. So it will be this dimension times the dimension at the back there, or this dimension, this dimension times that dimension, which will be the area, because you have a groove here. So it is the minimum dimension that you are having. This is how we report the values of toughness. Any questions, guys? We have finished the lab. I will stop here. So if you have any questions, otherwise you can leave. Any questions, guys? No questions.
سوينا لك ثواني ولا؟
We will have, and now let us focus on this lab. Do you have any questions, guys? because I need to stop the recording also, so that it does not take much time from the people who are doing this.